When you have an expression that requires a quadratic equation to solve, you can sometimes make an approximation that will simplify the equation. So recall that if Kc is a very small number, that means that there are a lot more reactants than there are products. So the concentration of reactants at equilibrium is going to be approximately the same as the reactants initially. So an approximation can be made if the initial concentration of the reactants are at least 100 times greater than Kc. We call this the rule of 100. So the way that we're going to use this rule is we're going to find the smallest initial concentration we have and divide it by Kc. If the number is greater than 100, we can make the assumption that the concentration of the reactants initially is approximately the same as what it will be at equilibrium. If it's less than 100, the assumption can't be made, and we would have to use a quadratic formula to solve the problem. So let's see this in action. We've got an example here of a reaction of nitrogen plus oxygen gas reacts to give 2NO gas. The initial concentrations of nitrogen and oxygen are 0.05 and 0.038 moles per decimeter cubed. The rate constant, the equilibrium constant is 4.2 times 10 to the minus 8. What is the concentration of NO in the mixture at equilibrium? As per usual, let's start with our balanced chemical equation. So N2 plus O2 gives us 2NO, and our ice table. So initially, we've got 0.085, 0.038, and 0. Our change, our nitrogen and our oxygen are going to go down by negative x. Our NO is going to go up by 2x. So we've got 0.085 minus x, 0.038 minus x, and 2x. Our Kc then would be NO squared over N2 times O2. And let's sub in what we know. So we got 4.2 times 10 to the negative 8 is 2x all squared divided by 0.085 minus x times 0.038 minus x. This is the point now where we want to check and see if our assumption is going to work. What we're going to do is, because 0.038 is our smallest initial concentration of reactants, we're going to use that 0.038 and divide it by Kc, which is 4.2 times 10 to the negative 8. If we did that, we get a very, very, very large number. Okay, that's greater than 100. So our assumption here we can use. And for IB, what you want to do is put in that because Kc is small, we are assuming that the concentration of N2 at equilibrium is about the same as N2 initially, and the concentration of O2 at equilibrium approximately the same as O2 initially. You need to have this statement in your answer in order to get full marks for this question. We can now simplify the N2 and the O2 concentrations in our Kc expression. So this minus X from these two concentrations is going to be very, very, very small. So we can get rid of it. That simplifies to 4.2 times 10 to the negative 8 equals 2x all squared over 0.085 times 0.038. Much easier to solve now. So if we solve for x, we get 5.8236, just going to keep some decimal places for now, times 10 to the minus 6. And then the question asks us for the concentration of NO at equilibrium. We know that from our ICE table it's going to be 2 times X. So 2 times 5.8 times 10 to the minus 6. For putting it to sig digs would be 1.2 times 10 to the minus 5 moles per decimeter cubed.